So we're here at the example table, and in this video we're going to be talking about the comparison test. So let's just state the test. It's actually two parts. So if the series from n equals 0 to infinity a sub n converges, and 0 is less than or equal to b sub n less than or equal to a sub n for some sequence of numbers b, then the series with the b sub n's, sum from n equals 0 to infinity of b sub n, also converges. If the series from n equals 0 to infinity of a sub n diverges, and this time 0 is less than or equal to a sub n is less than or equal to b sub n, again for some other sequence of numbers b, then the series from n equals 0 to infinity of b sub n also diverges. So what is this saying? Essentially, if we start with a convergent series, in this case the series from the a sub n's, and we have another series that's smaller than this one, term by term, then this one must converge. Also, if we have a series that diverges, and then we have another series that's larger than the original one, term by term, then this one must diverge. So you can think of this, if this thing converges, it converges to some number, and then this series, the b sub n series, is bounded above by it, so it can't go past this. It can't go past this thing. It can't escape and diverge. It's stuck. This is actually why we need to make sure that 0 is that all the terms b sub n and a sub n are greater than or equal to 0. Otherwise, this wouldn't necessarily be true. So we're stuck between 0. So the b sub n's are stuck between 0 and the value to which this series converges. So this thing must converge. Similarly, on this intuitive level, if the a sub n's diverge and this b sub n series is larger than the a sub n's term by term, well then the a sub n series, say, is here, b sub n series is here. This one is diverging off this way, so it's going to push the b sub n's off in the same direction. So this series must also diverge. One thing to be very clear about, if we want to use the comparison test to prove that a series converges, then we need to bound it above by a convergent series. It doesn't do any good to bound it below by a convergent series, because if we bound it, if b sub n is here and a sub n is here, and this thing converges, well, maybe this thing converges to this, or it could also diverge. So to use the comparison test to prove convergence, you need to bound the series you're given above by one that you know about. Likewise, to prove that a series diverges, say that b sub n diverges, we need to bound it below by a series that we know about, one that diverges. So let's take a look at some examples. So first, let's ask ourselves, does series sum from n equals 0 to infinity of 1 over 2 to the n plus 1 converge? So one of the things that you'll have to, one of the skills you'll have to develop to apply the comparison test is to look at a given series and say, well, to what series could I compare this? And in a case like this, I hope that you see something like 1 over 2 to the n, which is a geometric series that we know about. So since, let's see, so 0 is less than or equal to 1 over 2 to the n plus 1, which is itself less than or equal to 1 over 2 to the n, these are the terms that form a geometric series. So, and the sum from n equals 0 to infinity of 1 over 2 to the n converges, the series the given series, sum from n equals 0 to infinity of 1 over 2 to the n plus 1 converges by the comparison test. And whenever you're showing that something converges or diverges, it's always good to be specific about what test you're using. So what did we do? We took this series, we bound it above term by something we know about, something we know that converges. Remember, we bound it above by something that converges, which means that this series also converges. Wouldn't mean a thing if we bounded it below by a convergent thing. We could also bound it below by lots of convergent series, but that wouldn't tell us anything. Let's look at another example. So in this example, let's ask ourselves, does the sum from n equals 0 to infinity of 1.0001 to the n plus 1 over 2 to the n converge? So, if we're going to use the comparison test, we have to figure out a good candidate to which we can compare this. Now, the easiest thing here seems to be to compare it to either this series or this series. So the question is, to which one we want actually to compare it? Well, we know that this thing, these terms alone, ignore the 1 over 2 to the n, these form a geometric series, right? The ratio is 1.0001. These things also form a geometric series, 1/2 plus 1/4 plus 1/8, and so on. The key difference between these is that this one forms a divergent geometric series. This one forms a convergent geometric series. When we add the two together, what should we expect to get? Well, we're taking a divergent series here and making the terms even bigger. So we should expect this thing to diverge. That's almost an intuitive application of the comparison test itself. So if we get rid of this thing and compare it to this, well, we're bounding it below by a convergent series, which doesn't do us any good. Here, we can bound, if we get rid of this part, we can bound the original series below by this, which diverges, and that can tell us something. So since 0 is less than or equal to 1.0001 to the n, which is less than or equal to 1.0001 to the n plus 1 over 2 to the n, and the series from n equals 0 to infinity of 1.0001 to the n diverges, the series from n equals 0 to infinity of 1.0001 to the n plus 1 over 2 to the n also diverges by the comparison test. So those are two relatively straightforward applications of the comparison test. The first one, remember, we're bounding something above by a convergent series to show that it converges. Here we're bounding something below by a divergent series to show that it must diverge. I'll leave you with one question. So, does the sum from n equals 0 to infinity of 1 over 2 to the n minus 1/5, say, converge? Now, you might be tempted to approach this in the way that we approached the first example that we did, which is to compare this to 1 over 2 to the n. But remember, 1 over 2 to the n converges, and those terms are smaller than these terms, and it does no good to compare something that we hope converges like this. We expect this to behave like 1 over 2 to the n. How much could this minus 1/5 affect things? We expect this to converge, so we need to bound it above by something convergent. Bounding it below by something convergent doesn't help. So I'll leave you with the question, how, or is it even possible, to prove that this thing converges using the comparison test?